Stop guessing hybrid weights. RRF fuses BM25 and vectors without score scaling pain. By the end, you will understand how a simple rank fusion turns separate lexical and vector results into one stable winner you can trust. I'm Professor Pi, teaching search and IR with simple Python. Hybrid search comes up whenever users expect both precision on keywords and meaning from embeddings. Pure BM25 finds exact or near exact keyword matches. Pure vector search finds semantic neighbors. Each alone misses something. People try to hand-tune weights or normalize scores and end up brittle and data-specific. Reciprocal Rank Fusion, or RRF, is a pragmatic way to combine the two ranked lists without fragile score scaling. Qdrant is a purpose-built vector store that gives us a fast similarity search engine, so we do not reinvent indexing and nearest neighbor lookup. At its heart, RRF is simple. You take two ranked lists. You convert positions into small reciprocal values. You add them up. High-ranked items from either list get rewarded. One concrete mini example is 3 documents where a vector search picks one and BM25 picks another. RRF will often pick the doc that appears near the top in both lists. That makes it robust against wildly different score scales. The trade-off is you lose a bit of interpretability of raw scores, but you gain stability and simplicity. We will build a tiny toy pipeline. It stores 2-dimensional vectors in Qdrant, indexes 3 small documents, runs a vector query, scores the same corpus with a compact BM25 variant, and then fuses ranks with RFF. Nothing heavy. This keeps the idea visible and portable to larger systems. This snippet initializes a Qdrant client connection and provisions a fresh collection configured for cosine similarity. The variable C holds the Qdrant client pointed at localhost and call names a tiny working collection. Vector params with size 2 and cosine distance defines how Qdrant will store and compare vectors. The call recreate collection ensures a clean index by dropping any prior one and creating the new configuration. Finally, the code prints the collection name, so you can confirm the target index. Seeing created set to RRF demo confirms Qdrant is reachable and the collection is ready for inserts. Next, we put a tiny corpus into the collection so vectors and payloads line up. This example prepares a tiny corpus where the list docs holds 3 lowercase texts and vex stores matching 2D vectors. The list PTS uses point struct to tie each ID to a vector and a payload with the text field. The function enumerate creates consecutive IDs starting at 1, which keeps mapping simple across later steps. The C upsert call writes these points into the Qdrant collection configured earlier. Shorter vectors keep things readable, but in practice, you would store higher dimensional embeddings. The final print confirms how many points were indexed, so you know the vector side of the hybrid setup is live. Now, we will run a vector search against that collection to retrieve the nearest neighbors. This code issues a vector search to Qdrant using the list QV as the query vector. The function c.search retrieves the 3 nearest neighbors in the collection and returns scored points ordered by similarity. The variable res holds the ranked results, while top picks the best match. Each result includes the ID, the score, and any payload if requested. Here we only need the ID and score to anchor later fusion. Increasing limit can improve recall but will cost more latency and post-processing work. The printed ID and score show which vector match currently dominates and by how much. Next, we compute a simple lexical score over the same small documents, so we get a BM25 style ranking to contrast with the vector order. This example builds a simple BM25 style ranker on the local docs. The variable totes holds tokenized documents, and terms defines the query tokens. The dictionary df counts in how many documents each query term appears, and idf converts those counts into inverse document frequency weights. The list scores sums per term contributions using a compact BM25 variant with K1 set to 1.2 and no length normalization, trading brevity for clarity. Larger K1 increases the impact of high term frequency, while smaller K1 flattens differences. The printed ID and score identify the best lexical match, which will contrast with the vector result. Finally, we merge the two ranked lists using Reciprocal Rank Fusion and pick a fused winner. This snippet merges the Qdrant vector ranks and the BM25 ranks using Reciprocal Rank Fusion. The dictionary VR maps each result ID to its vector rank from Res, while BO orders IDs by BM25 scores, and BR maps them to lexical ranks. The parameter K controls how quickly deep ranks are downweighted. Larger values make Fusion depend less on lower ranked items. The dictionary F computes 1 divided by K plus reg for both modalities and sums them, producing a calibration-free hybrid score. The variable T selects the best fused ID. The printed fused ID and score show a stable hybrid winner without any fragile score weighting. In a real project, this maps directly. Swap two-dimensional toy vectors for modern embeddings. Use a higher dimensional vector param size, and push Qdrant to an instance close to your application. Use an approximate nearest neighbor configuration for large corpora, and run batch queries to keep latency predictable. The RRF logic stays the same and can sit in a small microservice that merges vector and lexical candidates. Recap. RRF is a rank-based fusion that adds reciprocal rank contributions. Use it when you want a simple, robust hybrid without tuning score scales. One caveat: it trades off score interpretability and can downweight rare deep signals that might matter in niche cases. Next step: tune the RRF parameter K and the BM25 K1 together, and measure retrieval quality on a held-out set. That one experiment often shows whether Fusion helps your collection. If practical IR tutorials help, subscribe and watch the rest of the IR videos.